Thanks for the invitation, Lorenzo, and it's my great honor to present my works at this workshop in the summer school. So from the list of speakers, you can see we have covered quite a few topics in tactile sensing. So for my presentation, so I will focus on vision and touch. And I made a little change about my title. So I make it an open question. So vision and touch, multimodal or cross-modal? So firstly, I'll give a brief introduction to myself. I'm Shan Luo. I'm from University of Liverpool. I'm leading a robotic lab called Smart Lab, and it's part of the Center for Autonomous System Technology. You may ask why is Smart Lab? It's because we have smart people in the lab. Just a joke. It stands for Swarm Smart Agent and Robot Technology Lab. And we focus on robotics technologies in the lab. So here is an overview of the topics I will cover in the presentation. So firstly, I will give a brief introduction to the motivation of my research. So why we should focus on vision and touch, and are they multimodal or cross-modal in us humans. And next I will give an introduction on sense of robots, sensors, both visual sensors and also tactile sensors. And I will introduce my works on object repetitions using tactile images and also integrated visual tactile perception, both multimodal and cross-modal. And at the end, I will give some future direction in this topic, interactive perception. So firstly, let's see some biological motivations on this topic. So we have this phenomenon in us humans. Synesthesia, we call it synesthesia. So for example, here we have a kitchen example. So I always use this kitchen example because we like cooking and, for example, fish and chips. When we enter one kitchen, we represent the physical world in our minds. So we use this sensing input, like vision, tactile sensing, and other sensory inputs, and we have this data to represent this physical world. And after that, we make actions, like we peel the potatoes, we cut the potatoes, and we make interactions with the physical objects or other humans in the kitchen. And we have communications with other humans in the kitchen. So in this process, we have different sensory inputs. Mostly we have vision and tactile sensing. They are also the main focus of our research team. And normally we combine them both to do some tasks. But sometimes we also cross-modal. We have cross-modal sensations for both vision and tactile sensing. So I will give you some example later. So we have these inspirations from humans. So we want to transfer these skills to robots to cook the meals for us or for themselves. So firstly, we need to have the sensors. Like we humans, we have vision. Like we have our eyes to project these views to our eyes. We have these repetitions in our minds using vision. At the same time, we have the human touch. So we have our skin. So using this skin, we can project these contacts or pressure distributions on our skin to our mind, and we have some repetitions of the physical world as well. But for our human brain, so we have this multimodal sensation. So there's some psychological experiments that show that both vision and tactile sensing can activate some same parts in our human brain. So it means we have multimodal sensation or cross-modal sensation in human brain. So for example, here we have different cortex for different sensory inputs, and some of these cortex parts, they're responsible for both vision and tactile sensing. So back to robotics. So we have the sensors for humans, so we're sensors for robots. So for human eyes, so they have cameras. So they have webcams, depth sensor, stereo cameras, and they have different repetition types. So like RGB data, depth data, or other data types in vision. So you may ask what sensors we have available for robot touch. we have many choices based on different sensing principles, like capacitive, or optical, or thermal effects, and many others. So here I won't go into details of these sensing principles, but you can go to further details in my review paper. I will show you later. But I will give a brief introduction, some categories of the tactile sensors. So in the last slide, you have seen these sensing principles. But for me, I would like to take myself as a user of tactile sensors. So I categorize these tactile sensors into different categories according to the applications. So firstly, we have these single contact, or we call it haptic sensors. We only have single contact with the objects. So for example, for these whiskers in mammals, so they get this single contact. Similarly, for robotics, so we have force sensors. Only for one point, we get the force values, force directions, or we have microphones. We have a pin to scratch on the surface like a table, and we use a microphone to get the vibrations. And we have single contact vibrations, and we take it as a touch. Similarly, we have artificial whiskers. It can get the single contacts with objects. So for these ones, they are very sparse and they get very little information from the physical world. Similar to our fingertips, so we have very high resolution textiles or tactile elements. So for example, here we have a human finger, and we have around 14 by 14 like sensing elements in our fingertip. So for this type of sensors, we have high spatial resolution sensors. So in this category, we have different tactile sensors based on different sensing principles. For example, these commercial ones, was robotics one, PPIs, or multimodal biotech. So they have multiple textiles in the sensor panel. So for these ones, most of them, they have a plane, and they have a range of sensing elements in the same panel. I would like to point out this gel size sensor, so one of the optical-based tactile sensors. We call it optical sensors, optical-based tactile sensors, or vision-based tactile sensors, because we are using a webcam in the sensor. So I will give more details in the next slide. So here we have the gel size sensor, that's the picture. And we have the scheme of the sensor itself. The sensing principle is quite simple. So we have a camera at the base, and we have a very soft gel layer on the top. So once we get in contact with the gel layer, the camera can capture the deformations of the gel layer. So for example, here we use our finger to press on this finger panel, and it can get our fingerprints. So using this tactile feedback, so we can facilitate different tasks in robotics. So for example, here we use a gripper, robotic gripper, to insert the USB into a mating hole. So if we have the tactile feedback, we can do it much better than without any tactile feedback. So for these ones, we have high resolution for the tactile sensors. So the third category in tactile sensors is large area tactile sensors. So we have seen the single contact and also the one similar to our fingertips. But we have skin covered on our body everywhere, right? So especially for like large area body parts, like our backs, legs, we have very sparse textiles in these areas. These areas are very curved, so we can't have these planary tactile sensors like the ones we have seen before for these body parts. So we have the different like modular tactile sensors or soft tactile sensors. I won't go into more details here, and I believe Paula will give more examples later. So as I said, I'm a user of tactile sensors, so I compare these sensing modalities, visual one and tactile. So for vision, we have global view of the physical world. And for tactile, we have very local observation of the physical world. But for information, we have very rich information from one visual image, but for tactile, it's very sparse. For computation, visual ones can be very high, but it can be very low for tactile sensing. And we have to tackle different variances in vision and tactile sensing. So we have rotation and translation for both tactile sensing and vision. And we have scaling for vision. But for tactile sensing, we don't have the scaling variance. So it means because we get direct contact with the objects, so we don't have the scaling problem. But we also have the illumination problem. We call it tactile illumination problem. It's because if we press harder, the pressure will be higher, right? So we call it tactile illumination. So for more details, you can go to my review paper. So next I will give examples how to use tactile sensors for robotics. So firstly, how to represent the physical world using tactile images. We call it tactile images, similar to the images captured by digital cameras. So again, the kitchen example. So what properties we can get from the tactile images? So we can get shapes, locations, textures, poses, so of the physical objects. So we can use the tactile images to represent these physical objects, so in different ways. So firstly, we can use the contact points. So we explore the object several times. We get these contact points and we construct the objects into 3D models, and we can recognize them. So for this method, we can recognize different shapes, any ones. But on the other side, it's very time consuming because we have to explore the object surfaces many times to collect these points. Another method is we can use bag-of-words framework. So for example, here we collect these tactile images and we extract the local features. So for example, here we can use image moments or like tactile shapes, descriptors, to describe these local patterns. Once we get these descriptors, we can represent these features into a histogram for different objects, and we can recognize these objects. So the advantage of this method is we can get the local features. But on the other side, we use the bag-of-words framework. We lose the information of 3D distribution. Is that possible to combine both? So we have 3D distribution and also local features. It is possible. For example, here we have a pair of scissors. We collect two types of data, so 3D sensor location and also tactile readings. Similar to the last work, we have this bag-of-words framework. We collect the features and we bag them into words, and we can get four-dimensional point clouds. So we have X, Y, Z locations, and we have one additional dimension, that is the words for the tactile feature. In this way, we have four-dimensional point cloud. So we match these point clouds and we can recognize these objects. And in this way, we integrate both location and tactile information. And in this way, we can get a better perception. So in the last few slides, we only see the tactile information or haptic information. So next, is it possible to integrate vision and tactile sensing? So like what we do in our daily life. So here I've collected some data from 100 pieces of fabrics. So we have camera images of fabrics, so on the top. We have gel side data on second line. So we can see some similar textures in both lines. So these ones. So it's similar to our own experience. So for example, for when we wear clothes, so we see these textures in our clothes, and we can feel these textures in our clothes as well. So in this work, we want to have an integrated perception using vision and tactile sensing. So this is the framework to integrate them into a latent space. So we use deep neural networks to extract the repetitions from both vision and gel set. And we maximize their correlations using maximum correlation analysis so that we have integrated latent space. So in this way, we can have enhanced perception of these textures. So in the last work, you can see we have this multimodal perception of these textures. But it is possible to have cross-modal perception. So we call it touching to see and seeing to feel. So it's very common in our daily life. We always, so again, the same example for fabrics. So we see these textures, and when we close our eyes, we may feel these similar textures, right? So there are some applications of this work. So in robotics, we can apply it in grasping and manipulation. So once we see one object and we get the visual features, and once we grasp the object and we can feel these features in our sense of touch. In this way, we can make the grasping more consistent. And also, for online shopping application, we can have this visual image and we generate some pseudo tactile sense, and the customers can feel the textures of clothes at home. So how to do this? So we have these tactile inputs and we encode it into feature space and we decode into a visual output. Or vice versa, we have a visual input and we code it into the latent space you have seen in the last work, and we decode into the tactile outputs. So here is a more detailed program for generating these pseudo outputs, like the tactile images or visual images. I will give some examples here. So for example, we have this visual input. It's a bit blurry here. And we can generate these tactile outputs. And here you can see this is a real tactile image from the fabric. So you can see this, there's some similar textures in the image, but you can also see is pseudo one, because these marks in the tactile image is not as good as in the real image. And similarly, we have the tactile image, and we can generate a visual image, so similar to the one we see in the real visual image. And by now, we have seen this multimodal perception and also cross-perception for robotics and also other applications. I have seen one speaker on fabrics as well, textiles, and I think this workshop can foster some collaboration opportunities. And next, I would like to say, to give some examples of interactive perception. So in the previous works, you have seen we always have this passive perception. We collect the data and we set up one latent space for vision and tactile sensing. But we don't have any action involved. So for interactive perception, we have these movements, we have these actions in this interactive perception. So what action we can have? We can have press, we can have sleep, and many others in manipulation tasks. One of the common settings for these actions, so we have the SLAM settings, right? We can do the localization and mapping in the environment. But what we always do is we have vision as the input. So we can have data, we can have visual sensors, cameras, but it's possible to have tactile as the input. So there are some pre-works using whiskers, so you have seen in the previous slides. So from this one, you can see this robot is moving around in this arena and is making contact with its objects. And after a while, it can create a map for itself, and it can localize itself in this arena. So we call it a haptic or single contact SLAM. It's possible to integrate vision and tactile sensing for this localization problem. So we call it visual tactile SLAM. So we have the interactive perception by interacting with the objects. So similar to previous works, we can have a shared feature set for both vision and tactile sensing. And here is an experimental setup. We have a 3D printed gecko, and we have the robotic manipulator to explore the surface of the gecko. And we can localize the contact of the tactile sensor on the surface. And we have a global view and a local view. So we have a global view of these objects using the visual image. So that's how we do. So we have a glance of the objects. So we have a global view. And then we have the context. So they are the local views of these objects. And we want to localize this context in this global map. So what we do is we have this recursive filtering framework to filter this possible contact location in these objects. It consists of 2 steps. So we have this motion updates and also overall updates. So it's very similar to the classic SLAM framework. Now we have the motion model. We use the Gaussian distribution to model the motions of the tactile sensors on the surface. We have these measurements models. So we have the global map, and we have the local view, that is the tactile image, and we compare these features from the local view and also the global map. And we can match these features, and we can localize the contact in this global map. Here's some outputs in the experiments. So here's a bench pass. So the tactile sensor is exploring these objects, and we are predicting the contact locations here. So we're predicting the most possible locations on these objects. So after a while, so we can localize its contact in these objects. So now we have seen some preliminary results using tactile sensing for interactive perception. But what is the future? So in the previous work, we still have these feature repetitions for tactile sensing and vision, and we update the motions. But we don't have the action and feature learning in the same space. So the next step is to leverage action in perception and also perception in action. So actually they are in the same loop. So we always use the actions to maximize the rewards from for the repetition learning. And also we have the repetition learning to optimize our actions. So actually they are in the same loop. And there's quite a few different applications for this work. So for example, we can have the robot to cook for us or for themselves. Right. So to wrap up my presentation, as you can see, the overall goal of the research is to enable robots perceive the physical world using both vision and tactile sensing. And there are some milestones on this route. So we have achieved the perception using tactile sensors. And we have the tactile object repetitions, so like local and global shapes, and also textures and poses. And also we have multimodal and cross-modal visual tactile perception. On the other hand, we are still have a long way to go for this intelligent perception. So we still need to involve interaction in this loop. So we have this intelligence perception through interaction for the future work. And I would like to acknowledge my collaborators across the world. Thank you, and welcome to questions.